All right, welcome multivariable calculus students. This is Dr. Sweeney. What we're going to do is we're going to start out by talking about vector calculus, and this is the very first section that we're going to be looking at when we look at multivariable calculus. The reason why is because one of the most common ways that we actually represent multivariable either systems or multivariable objects is by utilizing vectors, right? It's a representation that we're going to be utilizing for that reason. And when we talk about vectors, where we're going to start out is we're going to talk about vectors in 2D or two-dimensional vectors. Those are ones inside of the Cartesian plane. That's our XY plane. And we do that because it's easiest to kind of envision them, to kind of graph them, and to do work with them. We're going to take those two-dimensional ideas, and then we're going to kind of expand out. We're going to expand out into three-dimensional ideas, and then basically everything kind of moves out from there into multi-dimensions. Now, that's not always true when you get into higher level math, but for our purposes, it really does kind of work that way. You start out with 2 dimensions, right? And then you can kind of move quickly into more dimensions. So for our first section here, for vectors in a plane, we're going to be looking at, inside of my book, it's 2.1, we're going to be looking at these key questions. We're first going to ask ourselves, what is a vector? And then secondly, we're going to ask ourselves, how do we define vectors? We're going to kind of do that at the same time. Then how do we graph vectors? We're going to utilize those first two questions to do the third. Then how do we do algebra on vectors? Because once we've actually got a graphing way or a way to do geometry on vectors, we want to make sure that we have an algebra for them. And then we'll look at some alternative ways to define vectors, particularly using trigonometry. We'll talk about these things called unit vectors that are actually going to be really important for our work and will be really important for us to be able to do anything inside of vector calculus and multivariable work and calculus. And then how do we use what we've learned about vectors to work through some basic applications? So we're going to look at some basic physics stuff where what we do is we're going to look at forces and speeds and things like that are normally represented using vectors, and then we can utilize our basic vector calculus in order to talk about and do these problems. All right, so we're going to ask ourselves, we're going to have this question of like, what is a vector and how do we define a vector? So a vector is a directed line segment. And what we mean by that is that a vector is defined by two qualities, its direction and its magnitude. Okay, so what is a vector? Directed line segment, how do we define it? It is a direction and a magnitude. Okay, and a magnitude is going to refer to the length of the vector when we talk about it just in a basic graphing scenario, and in some scenarios length makes sense. But in other applications, it might be the amount of force being applied, it could be a speed, or some other quality of whatever system that you're looking at. Okay, now, the best way to kind of like start out with thinking about vectors is actually to start graphing them. So what we're going to do is we're going to imagine a Cartesian plane. Or actually, we're going to draw a Cartesian plane. And a vector, so it's a directed line segment, so every line segment's got to have a beginning and an end. And it's directed, which means that we're going to have a starting point, okay, which we'll call our initial point. So let's make this the initial point. And then we'll have a terminal point. And so there's our terminal point. And what we're going to do is we're going to draw a little arrow at the end of the terminal point. And so that's our directed line segment. Our initial point here is 2, 2. And our terminal point here is 5, 6. So that's our vector. It's the vector that goes from 2, 2 to 5, 6. And that's what we're going to define it as. Now, the direction, we'll talk about the direction, but basically you can think about the direction could be defined as this theta right there. Okay, so that might be thought of as the direction, that angle. Or we could kind of just think about it in space, and we'll define direction a little bit more clear. We'll clarify that a little bit more in just a moment. For the magnitude is the length of this vector. Okay, so we want to know the magnitude. And how we're going to write that is sometimes we might write it as an absolute value. So if we call this vector v, we want to know the absolute value of v. Okay. Or sometimes we might see it as with double lines, okay, as that's the magnitude of v. Okay? Notice as well, so v is the vector, and what I've done is I put a little line with a top arrow over the top of it. So this is your notation for a vector. That's how we write them. Sometimes what you'll also see is you'll see a bolded v. Now, a little bit harder when I'm actually writing on the screen, but a bolded V, if we actually have some kind of, if you're writing it in Word or you see it, it's been LaTeX or something along those lines, a bolded V will also be the notation for a vector. And when we write, for our purposes, when we write something like that, this is defining as the magnitude of v. And there's our notation. So you ask yourself, well, how do we find the magnitude of v? Well, what we're going to do is we're going to find our magnitude in this case is going to be called, it's going to be a Pythagorean distance. Okay, it's literally the length, and it's the length utilizing the Pythagorean theorem. So what you're going to notice here is you're going to notice that we got this length right there, and we got this length right there. And you can see that we can create a right triangle, okay, using those 2 points in space. And so the length down here is a length of 3. That's the length of our, on the x-axis. And the length on the y-axis is going to end up being 4. That's 3 and 4. And so the distance, my magnitude of v, which is that length, is going to equal the square root of 3 squared plus the square root of 4 squared, right? And it's called a Pythagorean distance because it uses the Pythagorean theorem. Okay, so there's your Pythagorean distance. And that's going to be important when we start looking at three-dimensional vector calculus as well, because we're going to use a Pythagorean distance there. We're just going to interpret it a little bit differently for 3 dimensions. So that's what we've got there. Now, you might ask yourself the question of, like, do I have to actually go in and, draw a triangle every time? And the answer is no. Because essentially what you're using here for the magnitude is you're using the distance formula. Okay? So remember your distance formula, d, is going to equal the square root of x1 minus x2 squared plus y1 minus y2 squared. That's your distance formula. And you'll notice that that's also the magnitude of that vector. Okay? So we've got the magnitude of the vector. Okay? So there we go. Well, here's a question. The question is this, is like, are there other vectors that have, or are there other, kind of directed line segments in space that in fact have the same exact magnitude and the same exact direction as this vector, as 2, 2 to 5, 6? Okay, and the answer is yes, there are. So like, let's say for example, I start out here, okay, so that's 1, 2, 3, 4, 5, 1, 2, 3, 4, okay, so that's going to end up being -5, -4. Okay, and if I go in here and I take it up, and this point right here, okay, this point here is -2, 0. And so now, if I make my initial point as -5, -4, and my terminal point as -2, 0, I now have a directed line segment. And the question is whether or not these two are what we call equivalent vectors. So we're going to ask ourselves, are -5, -4 and -2, 0 equivalent vectors? So the first thing that I can do is I can actually, let's call this vector w. Pardon me. And so our v, the first vector that we used here, and w equivalent. That is do they have the same magnitude and the same direction? So same magnitude, same direction. Okay? Now, what we'll do here is we'll kind of look at it and we'll say, okay, well, let's see. Okay, let's see. I'm going to go in and I'm going to first figure out the magnitude. So the magnitude of w, we're going to use that Pythagorean distance, and it's going to be the square root of -5 minus -2 squared plus -4 minus 0 squared, which is equal to the square root of -3 squared plus -4 squared, which is the square root of 25, which equals 5. And I know I didn't finish this up, but this magnitude right there, that magnitude actually turns out to be 5 as well. So what we see is that they have the same magnitude. Now, are they in the same direction? And so if I kind of go in here and I look at it, you can kind of see that they are, right? They're kind of pointed in the same direction in space. You can kind of eyeball it there. You can look at it. And you can see, oh yeah, you know what? They look like they are actually in the same direction. That's cool. We're going to get into how do we know, in fact, they are in the same direction in just a little bit. But the fact of the matter is that these two, they are in fact our equivalent vectors, right? We'll talk about the trig in just a little bit, but they are in fact equivalent vectors. And in fact, if we want to think about this, we can actually imagine a vector that is in fact, and by visual inspection, they are in the same direction. Like I said, we'll get a little bit more concrete about that in just a bit. So those two are equivalent. Now, let's do another example. One that, isn't a 3, 4, 5 triangle. So we'll take example number 2, and we'll have our initial point be at 1, 1, and we'll have our terminal point be down here at 1, 2, 3, 4, 5, 5, 3, or 5, negative 3, 5, negative 3, okay? So we're going to go from 1, 1 to 5, negative 3. And so what I'm going to do is I'm going to say, okay, well, what's the magnitude? So we'll figure that out. The magnitude of this one, we'll call it v again. The magnitude of v is going to equal the square root of, and we'll take 1 minus 5 squared and plus 1 minus negative 3 squared. And that's going to then equal the square root of negative 4 squared plus 4 squared, which is the square root of 16 plus 16, which equals root 32, which is equal to 2 root 4. So that's our magnitude. And then we'll have this other direction. We'll talk about that direction in a little bit. Now what I want to do is I want to actually create a vector, okay? Create a vector anchored at the origin. And this is actually going to be a really important vector. It's going to be used a lot inside of linear algebra. Okay, and we use it oftentimes to just talk about the vector in general, whichever this vector is. This vector v here happens to have this particular initial point and this particular terminal point. Let's imagine instead now that what we do here, okay, is we go and we generate another vector anchored at the origin. Okay, so now that's our other vector anchored at the origin. And you can go in and check. Okay, basically what I did was I went down 1 over 1, okay, down 1 over 1 in order to get to the origin, and so I did the same thing with the terminal point. I went down 1 over 1 with the terminal point. If you want, you can go in and check, right, that a vector that goes from 0, 0 to, in this case, 1, 2, 3, 4, goes down to 4, negative 4, is in fact, it has the same magnitude, right? And also you can see actually that it has the same direction, okay? That vector anchored at the origin is called the standard position vector, okay? So it's called a standard position vector, and it is an identical vector, just basically anchored again at the origin. Let's do another example of this. Do another example, draw a Cartesian coordinate plane. And we'll take a vector, and we'll have it start up here at 2, 4. And we'll have it go from 2, 4 to negative 1, 6. So 2, 4 and negative 1, 6. Okay, so you can see that it's actually pointing kind of like going to what would be the equivalent of the west. Now what we'll do is we'll create the standard position vector. Okay, so here's my standard position vector anchored at the origin. So to anchor at the origin, I went down 1, 2, 3, 4, down 4, and over 2 to the left. So I'm going to do that with my terminal point. So I'm going to go down 4, 1, 2, 3, 4. Okay, and I'm going to go over to the left 3, 1, 2, 3, because that's 1, 2, 3. Okay, so over to the left, or excuse me, pardon me. I'm going to go down 4, 1, 2, 3, 4, and over 2, 1, 2. Okay? So in order to generate that standard position vector, what I did was I took the initial point, okay, which in this case was 2, 4, and I moved it to the origin, and I clocked out how many, right? Okay, so I went down 2, or excuse me, down 4, okay, and I went left 2. And then I went to the terminal point, and I went down 4 and to the left 2, and that generated another vector in the same position, okay? in the same direction, right, with the same magnitude, but just anchored at a different spot. And I can do that with any of them. So like, let's say, for example, I want to start, I want to have my initial point, and we'll have my initial point at 1, 2, 3, 4, 1, 2, 3, 4, at -4, -4. So if I take a look, and what we could do is we can just actually, well, that would be going 1, 2, 3, 4, 5, 6. So that goes 6 to the 6 to the left. So I'll take my terminal point and go 1, 2, 3, 4, 5, 6 to the left. Okay, and it actually remains in the exact same location in terms of it doesn't go up or down. So it's just 6 to the left. So now my new vector, okay, or my equivalent vector, but in a new location, is right there. Okay, notice same length, same direction, and all I had to do was just basically figure out how it is that I moved the initial point, and then do that with the terminal point. So the next thing that we want to do is we actually want to utilize some trigonometry to characterize vectors. We want to use trig in particular because it allows us to create or to talk about those angles that help us to define the directions a little bit more concretely, and that are then going to allow us to do some applications. Okay, so let's take a look at it and take some examples, and let's just start out with a standard position vector. So we start out with a standard position vector, and what I want you to do is I want you to really think about, and we're going to use trig, and I want you to think about that unit circle. And one of those facts that we know about the unit circle. So essentially, that if, let's imagine that I have this line, okay, and it just goes out into space. There it is. It's going out into space, and it's got a length of, we're going to call its length b. Okay, so the length of that line is going to end up being b. All right. Now, what we want to know is, and you know, you might be able to go in and you're like, hey, I'm reading it, and I'm actually analyzing it at the moment, but I kind of made it a little bit less than for a couple different purposes. So there's that length b, and it's got an angle here called theta. Okay, it's got an unknown angle theta. So theta, okay, is the angle between the origin, okay, or actually the positive x-axis, that's what we should actually say, positive x-axis, and essentially the terminal ray of our vector. So there's theta. Now, if you remember, if like, say for example, let's just imagine that the length here was 1, right? So there's 1, if that length was 1, and so now we've got this length and this length, you want to remember that the length down here, okay, that x length would end up being cosine theta, and the length for on the y-axis would end up being sine theta. Okay, so when we utilize the unit circle, or we utilize something that has a radius of 1, okay, that's that radius of 1 from the unit circle, right? You got that unit circle, etc., etc. Then we have that sine theta is going to be our y value, and cosine theta is going to be our x value, right? So if, right, b equals 1, then x equals cosine theta, and y equals sine theta. Okay? Now, b doesn't necessarily have to equal 1, but there's a way that we actually, if you kind of remember back to your trig, in which we figured out how long was this, call this y2, and how long here was x2. Okay? So for a general b, remembering back to your trig, your x2 is going to just end up equaling b cosine theta. So it's going to be the length of, or the magnitude of that vector times cosine of the angle, and then y2 is going to end up being b sine theta. So this point right here is b cosine theta, b sine theta. And basically that's going to be how we're going to go out and figure out like the angle of the vector, okay, and relate it to that magnitude and actually to the values for the vector. So how do we use this? Let's actually look at one where we're going to utilize the standard position vector, okay? So we use standard position vector. We'll start at 0, 0, and we'll go out here. We're going to start at 0, 0, and we'll go out to 4, 2. Okay, there's 4, 2. And we can determine the magnitude of the vector, right? So that's the first thing, is find magnitude of v. And that's going to end up equaling the square root, and that's going to be 4 squared, okay, plus 2 squared, which is the square root of 16 plus 4, which is 20, which equals 2 root 5. So that's our magnitude. That equals the magnitude of v. Now we've got theta right here, okay? And what we're going to do is we're going to use the fact that x2, we're going to have b cosine theta and b sine theta. So the x value, or the length of the x side, is going to be b cosine theta, and the length of the y side is going to be b sine theta. So notice the length of the x side is 4. Okay, length of the y side is 2. So what that means is that 4 is going to equal, and b is our length, so b is our magnitude. So 4 is going to equal 2 root 5 cosine theta, right? So that's our x value. And you can actually just go in and utilize your calculator in order to find that. And so what we end up getting is we end up getting that cosine theta, when I divide by 2 root 5 to both sides, equals 0.8944, so on and so on and so forth. It's inside of my calculator. And so that means that cosine inverse of 0.8944 will end up equaling theta. Okay? Now, very important, notice it's not just that I've got cosine inverse of 0.8944, it's also, it's in the first quadrant. Okay? And so consequently, what I'm going to get is I'm going to get a theta that's going to be somewhere between 0 and 90. I don't have to actually do any kind of modifications. So what I'll do now is I'm going to take cosine inverse, and that ends up giving me, so theta ends up equaling, and this is in radians, 0.436 or 0.4636. Now if you do the same, you can do the same thing with the y values. So 2 will equal 2 root 5 sine theta. Okay? And if you do the same thing, you're going to see that theta, once again, is going to end up equaling 0.4636. In case you were wondering. The fact of the matter is that it's not going to change, right? Okay? The angle is the angle no matter which equation you use. Basically what we're going to do, right, okay, is you're going to go out, you're going to figure out what the magnitude is, and then you'll go in and you will figure out how long either x or y is, whatever that distance is, and then solve for theta. All right? Let's take a look at another example. Let's take a look at this example. So in this example, what we've got here is we're going to go from -2, -2, out to, and then this is 2, 4, 6, 8. So that's -8, comma, -4. So there we go. So in order for us to figure out, we're going to find theta, find the direction, okay, in terms of theta, or the angle. So we're going to start out, we're going to find v, or the magnitude of v, magnitude of v. And that's going to be, so the magnitude of v is going to end up equaling the square root of -8 minus -2 squared plus -4 minus -2 squared. So this ends up equaling -6 squared, or the square root of -6 squared plus -2, the square root plus -2 squared, which is going to equal the square root of 40, which equals 2 root 10. So we have 2 root 10 is the magnitude of v. And the next thing we're going to need to do is we need to go out and figure out theta. So if you remember, we're going to have an x is going to equal the magnitude of v cosine theta, and y will equal the magnitude of v sine theta. Okay? And so I'll just utilize x, the x direction. So this distance is 1, 2, 3, 4, 5, 6. So the distance is 6. Basically, your x is going to be your x2 minus x1. Right? So in our case, it's -8 minus and -2, just in case it's not a simple one to see. Okay? And that's an absolute value. So it's going to be 6. So 6 will equal, and this will then be 2 root 10 cosine theta. We'll start out, we'll take cosine theta, that'll equal 6 divided by 2 root 10. So theta ends up, cosine theta ends up equaling 0.94868. Okay? And now the next thing that I need to do, right, okay, is I need to figure out what theta is. So I got theta, I'm going to use theta is going to equal cosine inverse of 0.94868. But be careful, because notice it's not like it's in the first quadrant anymore, really. If you kind of move it over to the standard position, what you're going to see is you're going to see that it's now actually in the third quadrant, right? We've moved that, that vector over, okay? So it's now in the third quadrant, right? It's pointing basically southwest. And so what we're going to need to do here is we'll figure out what that value is, okay? Whatever that value is for cosine inverse. And then we're going to actually have to go in and calculate that difference from pi. So it's essentially going to be pi plus whatever that value is, whatever the value that we get back from our calculator. So I got cosine inverse of my answer. That's 0.321. And then I'm going to add pi to that. So when I add pi to it, so I've got theta, okay, ends up equaling 0.32175. And because I'm not actually in the first quadrant, I'm actually going to be here in this third quadrant, okay, the difference there is the difference of pi. Okay, that's the difference of pi. So my actual theta here is going to be theta plus pi. Okay, so that's going to be theta plus pi, which ends up giving me 3.46334. So how do we determine the direction of a vector as an angle theta? So one, the first thing that we're going to do is we're going to find the magnitude of v. Okay? Then two, we're going to let the x distance, okay, x distance equal, and this is going to be the magnitude of v cosine theta, and then we'll solve for theta. You can also use, okay, y equal to the magnitude of v sine theta. That's also allowed. And in either case, you're going to be solving for theta. What you want to do, though, is you want to remember the quadrant that theta is in. And that's going to end up being really important. So where we're going to look at next is we're going to start looking at these standard position vectors and then start working with algebra on vectors. Because a lot of our algebra on vectors, we're going to be utilizing the standard position vectors or transforming things into standard position vectors so that we can then work on or express the algebra between vectors. So let's start out with some standard position vectors. Okay. And what I'm going to do is I'm going to say, okay, so I'm going to start out with this one and this vector here, it's going to be the vector 1, 1. Okay. So it's going to go from 0, 0 to 1, 1. Its initial point is 0, 0. Its terminal point is 1, 1. What we're going to do, because it's a standard position vector, we can actually just define the vector as just 1, 1. Okay? Since it's going from 0, 0, like the length of the x value is 1, and the length of the y value is 1. Okay? So that standard position vector, we're going to get some new notation, and that new notation is going to look like this. It's going to have a bracket, or it's going to have like basically greater than or less than signs, or vector notation, and it's going to look like that for on the left-hand side, and it'll be 1. That's the distance from the origin to the x value, and 1 is the distance from the origin to the y value, right? Okay, position x, position y, just like the Cartesian coordinates. Notice, right, this new way of stating it, and we're going to call that now v. Okay, so there's our vector v as a standard position vector. If you see it written like this, this means that you're starting at the origin, okay, and you're going out to whatever that point is, and it'll be in that direction. So for example, this vector right here, okay, is negative 2, 4. Okay, so we'd write that as negative 2, 4. There's another standard position vector utilizing that vector notation. This vector here, is going to be -4, -5. So there's -4, -5. The origin is itself a vector. Okay, so the origin, that point, it has a standard position vector, and it's the position vector of 0, 0. Okay, it has 0 magnitude, right? If you calculate the magnitude of the origin vector, it's going to have a 0 vector, 0 magnitude. Okay, and there's our standard position vectors, and that's how we write standard position vectors. These are going to become really important or really crucial because they're going to allow us to do some algebra. There are two basic operations when working with vectors. One's called scalar multiplication, and the other one's called addition. Geometrically, scalar multiplication is thought of as compressing or expanding. So let's say, for example, I start out with this vector, and the vector is, in this case, the standard position vector here is going to end up being 3, 2. And let's say I double its length. Okay? I double its length, so now I have a new standard position vector of 6, 4. That's the vector with double the length of 3, 2. Okay? All right? What I'm going to say is that 2 times 3, 2 equals 6, 4. And you can see that geometrically. Okay? All right? 2 times 3, 2 equals 6, 4. Notice this thing here, the 2, we call that a scalar. And that's why this is called scalar multiplication. We're going to scale. And when we scale algebraically, we multiply the components of the vector, which is in this case 3 and 2, those are called the components of the vector, by the scalar to get our new vector. Okay? And we call that scaling. It's going to end up being called scaling. Okay? These two vectors, they are equivalent vectors now. 2 times 3, 2, and 6, 4, they are going to be equivalent vectors. Now, the thing about it, and we'll see this in just a little bit, is that these two vectors are also what we call, they're in the same direction. Now, it's kind of obvious that they're in the same direction. They have, that's that theta, and you can imagine if we take, look at 6, 4, it's got the same theta, right? Okay, it's in the same direction. So the thing about this is that scalar multiplication does not change direction. It maintains direction. And rather logically, what it does is it actually scales distance or scales length. Okay? It increases or decreases magnitude. So it's going to increase or decrease magnitude. And let's actually just take a look at by how much. You might be like, well, I wonder how much. By how much? And you're like, I certainly hope it doubles it. Right? So let's take a look, and let's say, for example, we take our standard position vector, and whenever we have standard position vectors, they're really easy to find lengths. That's going to be 3 squared plus 2 squared, right, which is equal to the square root of 13. And then, so that's our first vector, so we'll call that v. And then we'll take 2 times v, which we already know to be 6, 4, and so that's going to be the square root of 6 squared plus 4 squared. Okay, and that ends up equaling the square root of 36 plus 16, which is 52, which strangely enough, or not strangely enough, is 4 times 13, which is 2 times the square root of 13. Oh snap, okay? So, if we multiply a vector by a scalar, call our scalar c, then the new magnitude is c times v. All right, so the direction remains exactly the same, right? We don't get a change in direction, but our new magnitude is now just a scalar, what we call a scalar multiple of the old vector, we get a new vector, which is a scalar multiple of the old vector, and then we have just increased, increased the magnitude or decreased the magnitude by a multiple of c. Let's take a look at another example, okay? Geometrically, let's take the example of, and we're going to have -1, we're going to have 1, -1. So that's that 1, -1. And what I'm going to do is I'm actually going to go in and I'm going to flip this. I'm going to scale it. So I'm going to scale, and I'm going to take -2 times, or actually I'm going to take -3. Let's take -3 times 1, -1. We're going to go in, we'll multiply by each component. So this gives me -3, 3. which is great. And when I draw that as a position vector, that's going to be 1, 2, 3, negative 3, positive 3. Okay? Something happened. Okay? Well, here's the thing. Scaling compresses, okay, or it either shrinks it or expands it, but also it can also flip, okay, flip the vector. Now, this does change the direction from the perspective of what theta is, right? It actually changes it by a factor of pi when we're talking about radians. But in many cases, like in linear algebra, we're going to see that these vectors are pretty much the same. They're on, like, they are what we would say are on the same direction. They're what we call scalar multiples of each other. And so what you can see here is you can see this. You can see, okay, well, it's now just been reflected. It's been reflected over that origin, right? It's just pointing in essentially the opposite direction. So at first, we were going southeast, and now we're going northwest, which is the exact opposite, okay? So scaling by a negative reflects. And if we look at our magnitudes, so the magnitude of our original v is going to equal the square root of 1 squared plus negative 1 squared, which is root 2. And now, if we take v times negative 3, the thing is that we're going to actually have to do this by an absolute value, because you're squaring things, you're taking the square root. And you'll see that we've got the square root of negative 3 squared plus 3 squared. So don't forget, it should be positive. And so that's the square root of 9 plus 9. That's root 18, which is equal to 3 root 2. And so we've tripled the length. We've tripled the length. Okay, so the negative reflects and the magnitude is tripled. And that's how scalar multiplication works. Okay, so now let's talk about the addition of vectors, which we're going to call the quadrilateral method, or what we might also call tip to tail. So we're going to look at these with standard position vectors. You can also do this using, well, any kind of vectors that you want, okay? Basically, the method works no matter how it is that you do it, okay? So like, let's say, for example, I have v, and we're going to say that v is this vector right here, okay? And so there's v. And then we'll have w, and let's say, for example, that w is this vector right here. There's w, okay? And it goes up 2 over 2. And there's w into the negative direction. What we'll do in order to add v plus w is we're going to go in, and we are going to go basically up 2 over 2. We're going to essentially go in the direction of w, the length of w. Okay? So there's now w if it's moved over to the tip, this thing here called the tip, and we put its tail, and that's its initial point, its tail, the tail of w to the tip of v, and we create a new vector. And this vector right here, that is v plus w. Okay, that's called v plus w. We'll call that tip to tail. It's called quadrilateral because it turns out that it doesn't matter whether or not you add v first or you add w first, okay? So like, for example, if I have w and I take w and here's w, right? Okay, so we start from the same initial point, and then I add the length of v, okay? There's the length of v. I get to the same place. I get the same exact vector, okay? I get the same exact vector. We're all good, okay? The only thing that matters is really going to matter is that, like, for example, if I want to do w plus v, w's out here, right? Its position is way out here, okay? So plusing v, all right, would add something that looks kind of like that, okay? So here's v. So now this vector here out in space, okay, that's our new vector. Call that now w plus v, all right? And it basically just says, okay, which one are you starting with? Are you starting out with w or are you starting out with v? That's it, okay? Now, the thing is that if we use standard position vectors, things get a lot easier, okay? Things get a lot easier, and here's why. So let's take a look at this particular example, and it's going to be 1, 1 plus negative 3, 2. And we're going to imagine that both of these are started at the origin. Now we're going to utilize the same basic concept or principle. We'll start out at 1, 1. So here's 1, 1, and we'll call that our vector v. And then what I'm going to do is I'm going to go -3, 1, 2, 3, so negative direction 3 and up 2, right? My x is 3 and over 2, and I end up here, okay? And so my new vector, my additive vector here, okay, is the vector -2, +3, right? It's -2, +3. That's my new vector, okay? And it turns out that that one there is v plus w. We did v first. We went out on v. Okay, we'll actually do this. Put a little color to it. We went out on v, and then went out on w. That's our move. Okay, and you can see what we're going to do when we add is we'll add component-wise. So this is a 1. This is a -3. So 1 plus -3, and 1 plus 2. And so that ends up being -2, 3. And that's our new vector. Now, the thing about it is you might notice that since we're using standard position vectors, the order that I do it in isn't going to matter at all. It isn't, and it really won't, okay? Because let's say, for example, I go out on w first. Let's do -3, 2. So 1, 2, 3, 2. There's -3, 2. Okay, let me just erase this to make some space. So there's -3, 2. There's w. And then I go up 1 over 1 to get 1, 1 using my tip to tail method. And so there's v moved over. And so I end up at the same place. And this is how we end up with the real idea of the quadrilateral method. The quadrilateral that's created here, okay, right, it gets me to the same place. It still gets me to -2, 3. So if this was v and this was w, okay, so v plus w we saw was equal to -2, 3, and it makes sense that w plus v is going to equal, okay, -3 plus 1 and 2 plus 1, and since addition is what we call commutative, that's going to be -2, 3 as well. So no matter what order that you write it in, you're going to end up getting the same exact vector. Now here's the thing. When we're doing with standard position vectors, the addition of vectors is commutative. All right? If we're using vectors that are out in space, that are unanchored to the origin, you're going to have to determine which vector you're going to start with, okay? And then you'll add your new vector tip to tail, okay? And it's going to actually give you a different position, but the vector is going to be equivalent. In both cases, okay, you can see, I'll use some highlighter, this vector and this vector, they are in fact equivalent vectors. So that vector, those two vectors, they're not actually different vectors, they're just located at different positions. Okay, so when we're unanchored to the origin, when we're not using standard position vectors and you're adding, okay, you can still add tip to tail. You just got to consider the new position. If we're using standard position vectors, you can add them in any order that you want. It's completely commutative, right? And in all cases, those vectors are going to end up being equivalent, no matter how it is that you add them. Okay. So basically, addition of vectors is what we call commutative. That is you can add in any order. All right, add component-wise, and that's probably the easiest way to do things when you're actually going in and you are using these standard position vectors. By the way, it's not such a terrible thing to go. You can do the same thing pretty much here too. Okay. So if we look here, so one thing that I want to kind of bring up, because you might actually see it, is that another way to describe our standard position vectors, the ones that are in fact anchored at the origin, is to say that they're in component form. That is that they're written as the length in the x direction and the length in the y direction. So you'll notice if I write 1, 1, right, okay, that's 1 in the x direction, okay, and we have 1 in the y direction. So if you see that statement, that is that, or you see somebody referring to something in component form, they're basically talking about standard position forms, or the standard standard position vector in terms of in an algebraic term. So the last thing that we're going to look at before we start actually talking about the applications for our vector calculus in 2 dimensions is we're going to talk about these things called unit vectors. And they're going to end up becoming really important. So you want to get some practice. You want to understand what they are. So a unit vector is a vector of length 1. That's what we mean mathematically when we talk about unit. A unit length is a length of 1. When you're thinking about units and you're thinking about vectors, you should also be thinking about the unit circle, right? Unit being a length of 1. Hence, unit circle, unit vector, that's the idea. It's actually really simple to figure out what the unit vector is. A unit vector is transformed, or a vector can be transformed into a unit vector by dividing the vector in component form by its magnitude. So basically, what ends up happening, right, is you can just imagine that we've got, right, v here. Say, for example, I've got v, and v equals -3, 2, okay, times some scalar, call it a, okay, times some scalar, okay, and then there's a vector here, all right, and that scalar a, we'll call that's actually the magnitude v times some other vector right here, and that's actually equal to v cosine theta and v sine theta, right? Okay, we actually saw that before when we were working with trig. So if I actually pull out the v, right, I go through and I actually like factor out the v, what I'm going to end up with is I'm just going to end up with the cosine theta here and the sine theta, okay? And these, okay, they're from the unit circle. So they have unit length. That's the idea. They've got unit length, all right? So basically what I'm going to do is I'm going to go in and I'm going to factor out the magnitude v, and the way that I do that is I basically just divide through by v. That's all, okay? So let's say, for example, I have -3, 2. So I'll go find the magnitude of v, and that's equal to the square root of -3 squared plus 2 squared, okay, which is the square root of 9 plus 4, which equals root 13. So my unit vector, we'll call that u of v, all right? Call it a unit vector, call it u, and we're going to call it the unit vector of v. And so that's going to end up equaling, it'll be 1 over the square root of 13. We're going to divide through by, and then -3, 2. And so algebraically, that's going to be -3 over root 13 and 2 over root 13. Another way to go about doing this is actually to go through, so that's it. It's pretty simple to construct a unit vector, all right? Now, one thing we might want to do is we might actually want to like kind of do something, maybe like write it in a different direction, or we might actually go in and find a vector of a particular length but in the same direction, okay? So another way that we can do this is to notice that if I can find theta, then the cosine theta sine theta is also the unit vector, okay? By the way, let's go in. I'm going to write these out as a decimal so you can see exactly how things are working. So now, if we go in here and we say, okay, well, I want to figure out what that theta is, because maybe that's a different way or a different approach that I've got. So what I'll do is I'll essentially say, okay, well, I got, say, -3 is going to equal, I already know the magnitude, so remember that's going to be root 13, and it's going to be cosine theta, okay? So I got -3 equals root 13 cosine theta, and so that's going to then be -3 over root 13 will equal cosine of theta, okay? And then that actually gives me that theta ends up equaling, and when we plug it in, we get theta equals 2.5536, essentially. 2.5536. And then if we go in and we plug that in, right, okay, cosine of that 2.5536, okay, it should make absolute sense. It's going to end up being negative root 13. And then sine of that 2.5536, okay, is going to end up equaling our 0.5547, okay? And so we end up getting the same exact thing. We get negative 0.832 and comma 0.5547, and that's our unit vector, okay? So we can actually go either way. The easiest way is just to go find that magnitude and then figure out and then divide the vector, divide all the components of the vector by the magnitude. And that actually gives you your unit vector most easily. So let's look at an application that we've got here, that because sometimes what we want is we want a vector that's in the same direction, right? So every vector here is going to have a direction given by that angle there, right? That 2.5536. What happens if I want to actually have a vector that it has a magnitude of like 8? Okay, so like let's say for example that's what I want, right? So direction of V, and we'll call it W, the magnitude of W is going to equal 8. Well, the simplest thing to do is to just go in and multiply the unit vector by 8. Okay, so W, because it's going to be in the direction of V, it's going to have the same exact angle, so it's going to be like this one, okay, except it's going to be 8 times as long, because, right, the length of this vector, the length equals 1. So the length of W is going to be 8 times that 1. So W is just going to be equal to 8 times, in this case, negative 0.832, comma 0.5547. We go through, we do that multiplication. 8 times negative 0.832, and that equals negative 6.656, and then 8 times 0.5547 is 4.4376. And that is a vector that's in the same direction as V, but has 8 times the length, or it has a length of 8. Okay, this has a length of 1, all right, and W now has a length of 8 because we just took the vector and multiplied it by 8. So let's say, for example, we have a problem like this. We want to find a vector with a magnitude of 5 in the opposite direction of V. And so V is 8, negative 1. So what we're going to do first is we're going to find U of V, like our little unit vector for V. And so remember, the first thing that we need to do there is we need to find the magnitude of V. So the magnitude of V is going to equal the square root of 8 squared plus negative 1 squared, all right, which is the root 65. So there we go. And then the unit vector, so U of V is going to equal then 8 over root 65, comma, negative 1 root 65. There it is. There's our unit vector. We're just going to go in, we'll divide through by the magnitude. Great. So now we want our new vector to have a magnitude of 5, but we want it to be in the opposite direction of V. To be in the opposite direction of V means to, right, multiply by negative 1. So in order to do that, what we're going to need to do, too, is we're going to take negative 5 times 8 over root 65, comma, negative 1 over root 65. And so we're left with negative 40 over root 65, comma, 5 over root 65. So it's pretty much a step-by-step process, right? If you want to actually get a vector with a particular magnitude, all you need to do is transform it into a unit vector and then multiply the unit vector by whatever the scalar is. Okay, and remember this thing here, that's called a scalar. So this actually finishes the foundations that we have for vector calculus. We've actually gone over quite a lot. But what we've looked at mostly here is notation, some of the basics, the adding, subtracting, the multiplying, the adding and the multiplying. What it means to multiply by a negative number. How do we get these things called unit vectors? How do we, find the angles that we've generated or that we need to generate from a vector? How do we figure out what their angle is coming off of the positive x-axis? And also, making some relationships here between the work that we're going to do in calculus and some more trig. So you're going to see we're going to actually be doing a lot more trig too as we work with vector calculus, because we're looking at angles, we're looking at positions and directions, okay? In my next mini video, I'm going to be talking about some applications that we have for our vector calculus. So this actually completes our lecture.